Today, we will explore the technical architecture of a modern dual-fuel power plant and how its major systems work together to deliver reliable power generation. At a high level, the plant consists of three main zones. First, the fuel handling area, where LNG and diesel are received, stored, and processed through the regasification and fuel supply systems. Second, the powerhouse, the core of the facility, where the dual-fuel engines operate together with supporting utility systems. Finally, the control and electrical distribution zone, where automation systems monitor plant operation and power is exported to the grid. With this overall layout in mind, let us move into the operating principle of the dual-fuel engine. Moving inside the powerhouse, let us now focus on the operating principle of the dual-fuel engine. This slide shows the two combustion modes within the same engine architecture, gas mode and diesel mode. On the left is gas mode, operating on the Otto cycle. Natural gas is mixed with intake air through the gas admission valve, while a small amount of pilot diesel initiates combustion inside the cylinder. On the right is diesel mode, operating on the conventional diesel cycle. In this mode, the gas system is isolated, and combustion relies entirely on direct diesel injection into compressed hot air. This dual-fuel configuration enables seamless fuel switching while maintaining reliable operation and high thermal efficiency. Next, we will examine how the engine automatically transitions between these operating modes during actual plant operation. Now, let us examine the control logic behind the dual-fuel operation. Under normal conditions, the engine operates in gas mode while the control system continuously monitors gas supply pressure. If a gas trip or pressure drop occurs, the system automatically transfers the engine to diesel mode. During this transition, the gas system is isolated and diesel injection immediately takes over combustion without interrupting generator output to the grid. This seamless changeover capability ensures stable and reliable power delivery during abnormal gas conditions. Next, let us see how LNG is conditioned before entering the engine fuel system. This slide highlights the LNG receiving and regasification system at the plant boundary. At the jetty area, LNG is unloaded from carrier vessels through specialized marine loading arms, designed for safe cryogenic transfer at -62 degrees Celsius. The LNG is then stored and routed to the regasification system, where heat exchangers convert the liquid LNG back into gaseous form. During this process, the system controls gas temperature and pressure to ensure stable fuel conditions before the gas is delivered to the powerhouse. Next, let us move to the gas valve unit, the final safety and control stage before the fuel enters the engine. After regasification, the gas enters the gas valve unit, or GVU, the final safety and control stage before the engine. The GVU regulates gas pressure and manages fuel isolation through a double block and bleed valve arrangement. During an emergency trip, the shutoff valves close immediately while trapped gas is safely vented to prevent hazardous accumulation. The system then stabilizes the gas pressure before distributing fuel to each cylinder through the gas admission valves. This controlled fuel delivery enables stable combustion and reliable engine operation in gas mode. Next, let us look at the independent diesel fuel system that supports backup operation. With the primary gas path covered, let us now focus on the backup diesel system designed to ensure continuous power generation. Diesel fuel from the day tank enters the fuel conditioning skid, where redundant pumps maintain reliable fuel circulation, while automatic filtration systems remove contaminants continuously during operation. The fuel then passes through a shell and tube heat exchanger, utilizing the HT water circuit to maintain the required fuel temperature and viscosity before engine injection. Before reaching the engine, fuel consumption is monitored through a Coriolis mass flow meter, while the entire skid operation is automatically controlled by the local PLC system. This fully conditioned and continuously primed diesel line enables seamless transfer from gas mode to diesel mode whenever required. In gas mode, the engine requires a small amount of pilot diesel to ignite the air-gas mixture inside the cylinder. This function is handled by the pilot fuel common rail system. A dedicated high-pressure pump supplies diesel into a common rail, where fuel is distributed to each cylinder injector. The pilot injectors then deliver a precise micro-injection of diesel to initiate stable combustion across the engine. Next, let us look at another critical utility system, the compressed air system, used for engine starting and operation. The compressed air system supports two critical functions within the power plant: engine starting and pneumatic control. High-pressure air compressors charge the air receivers to provide starting air for the engine. During startup, this compressed air is injected into the cylinders to rotate the crankshaft until the engine reaches firing speed. A separate branch supplies clean and dry instrument air for pneumatic valves, actuators, and safety control systems across the plant. Next, continuous operation of the dual-fuel engines generates significant thermal energy, requiring an efficient cooling system to maintain stable operating conditions. The plant utilizes a dual-circuit HT and LT cooling system connected to the external radiator array shown here. The high-temperature, or HT loop, removes combustion heat directly from the engine block and cylinder components before rejecting the heat through the radiator fans. In parallel, the low-temperature, or LT loop, cools supporting systems such as lube oil and charge air to maintain engine efficiency and performance. After cooling, the water is circulated back to the engine through the cooling water pump system. To maintain long-term reliability, this entire cooling network also depends on proper water treatment and quality control. To support the engine cooling system, the plant utilizes a dedicated water treatment and demineralization plant to produce high-purity water for the closed cooling loops. Raw water first passes through ultrafiltration and reverse osmosis systems to remove suspended solids and dissolved salts. The water then enters the demineralization stage, where remaining minerals and ions are removed before being stored as demineralized water. This high-quality water helps protect the cooling system from scaling, corrosion, and long-term performance degradation. With the fuel, air, and cooling systems covered, let us move to the final supporting utility, the lube oil system. To conclude our technical overview, let us look at the lube oil system, a critical utility that protects the engine from friction, wear, and excessive heat during operation. Before engine startup, an electric pre-lubrication pump establishes oil pressure throughout the engine. Once the engine reaches operating speed, the mechanically driven main lube oil pump takes over continuous oil circulation. The oil then passes through filters and the lube oil cooler, which is supported by the LT cooling system, before being recirculated back to the engine. This combination of reliable lubrication, filtration, cooling, and monitoring helps maximize engine reliability, performance, and operational life. That concludes our overview of the dual-fuel power plant systems. Thank you for your attention.